The Big Bang Theory in 10 minutes. How our universe came to be. Planck Epoch. T equals 0 to 10 to the power minus 43 seconds. The universe came into being 13.8 billion years ago. It was compressed into an unimaginably small volume of space and began as an infinitely hot dense fireball. This state of affairs is described as a singularity. It is hypothesized that at this time, space-time is extremely turbulent and warped, giving it a Fermi character. The space-time foam is also known as quantum foam. Within this high-density environment, a quantum fluctuation can give rise to an entire universe such as ours. During the Planck epoch, all the forces are unified as one fundamental force, supergravity. When our universe bursts into existence, there is a sudden and rapid stretching of space everywhere. Grand Unification Epoch. T equals 10 to the power minus 43 seconds to 10 to the power minus 36 seconds. As space stretches and cools, it crosses a transition temperature where gravity separates from the other forces. Electromagnetism, the strong nuclear force, and the weak nuclear force then act as one single force, the grand unified force. During this epoch, the earliest elementary particles and antiparticles are created. Inflationary Epoch. T equals 10 to the power minus 36 seconds to roughly 10 to the power minus 32 seconds. As space continues to stretch and cool, it crosses another transition temperature and the strong force separates from the electroweak force. This separation triggers a period of exponential faster than the speed of light stretching of space, known as inflation. Einstein's theory of relativity says that nothing can move faster than the speed of light in space, but that does not preclude space itself from stretching faster than the speed of light. The stretching is caused by a repulsive form of gravity, and the universe doubles in size at least 100 times, going from the size of a billionth of a proton to the size of a grapefruit. Inflation ends when the repulsive energy decays into ordinary matter and energy, at which point ordinary Big Bang expansion takes over. The elementary particles created during the Grand Unification Epoch exist as a hot, dense quark-gluon plasma that is distributed thinly across the universe. Electroweak Epoch. T equals 10 to the power minus 32 seconds to 10 to the power minus 12 seconds. As the strong force separates from the electroweak force, particle interactions create a large number of exotic and theoretical particles with unusual properties. An example of such a particle is the tachyon, a theoretical particle that travels faster than the speed of light. Electroweak symmetry breaking and the quark epoch. T equals 10 to the power minus 12 seconds to 10 to the power minus 6 seconds. The Higgs field is a quantum field that permeates all of space. Particle interactions with the Higgs field impart particles with their mass, and the Higgs boson is the local excitation of the Higgs field. The Higgs field causes electroweak symmetry to break, resulting in the electromagnetic force and the weak force manifesting themselves differently. As the universe cools to below 10 quadrillion degrees, quarks, electrons, and neutrinos, along with their antiparticles, form in large numbers. The four fundamental forces assume their present forms. During this epoch, a process known as baryogenesis creates an asymmetry in the creation of quarks and antiquarks, which results in slightly more quarks being produced. There is an extra quark created for every billion quark-antiquark pair. When quarks and antiquarks make contact, they annihilate each other to produce energy, and the surplus quarks will go on to form all the matter that we see in our universe. Hadron Epoch. From 10 to the power minus 6 seconds to 1 second. As the temperature of the universe cools to 1 trillion degrees, the quarks combine to create protons and neutrons. Composite particles made up of quarks such as protons and neutrons are known as hadrons. In the extreme conditions of the Hadron Epoch, electrons can fuse with protons to form neutrons giving off neutrinos. During this epoch, some neutrons and neutrinos also recombine to form proton-electron pairs. Random combining and recombining is commonplace during this epoch. Lepton Epoch. From 1 second to 3 minutes. At the end of the Hadron Epoch, the majority of hadrons and antihadrons annihilate each other. Leptons and antileptons now dominate. Electrons come into contact with their antiparticles, positrons, to create energy in the form of photons, and photons collide with each other to form electrons and positrons. 10 seconds after the Big Bang, the temperature of the universe falls to a point at which new lepton-antilepton pairs are no longer created, and most leptons and antileptons are eliminated in annihilations, leaving a small excess of leptons. Nucleosynthesis, from 3 minutes to 20 minutes. The temperature of the universe falls to 1 billion degrees, and for the first time, atomic nuclei can begin to form. Protons and neutrons combine through nuclear fusion to form the nuclei of the simple elements of hydrogen, helium, and lithium. After about 20 minutes, the temperature and density of the universe has fallen to a point where nuclear fusion is no longer possible. Photon Epoch, from 3 minutes to 240,000 years. The universe is filled with a hot opaque soup of atomic nuclei and electrons. The photons left over from the lepton-antilepton annihilations from the lepton era are scattered by these nuclei and electrons, so visible light cannot move freely. Recombination and decoupling, from 240,000 years to 380,000 years. As the universe cools, free-roving electrons are captured by the atomic nuclei to form electrically neutral atoms via a process known as recombination. As a consequence, the photons in the universe are finally able to travel freely, and this event is known as decoupling. For the first time, the universe has become transparent to light, i.e., allows photons to travel freely through it. By the end of this period, the universe is filled with a fog made up of 75% hydrogen atoms, 25% helium atoms, and just traces of lithium atoms. The Dark Ages, from 380,000 years to 150 million years. The period between the formation of the first atoms and the first stars are referred to as the Dark Ages, even though photons were present at this time. The Dark Ages are so called because no sources of illumination, i.e. stars, existed during this time. In this period, cold dark matter dominated the universe. Cold dark matter is a hypothetical form of matter that we currently don't know much about. What we do know is that its gravitational pull is required in addition to the gravitational pull of ordinary matter for stars and galaxies to move in the universe the way that they do. It is estimated that in the universe, for every kilogram of ordinary matter, there exists 5.5 kilograms of dark matter. Reionization, 150 million years to 1 billion years. Over time, gravity pulls matter together to create the first quasars via gravitational collapse. The UV radiation emitted by these quasars stripped the hydrogen gas atoms of their electrons, creating an ionized plasma. This process means the gaseous fog is lifted around the quasars, and as a result, transparent bubbles form within the universe. Star and galaxy formation, 300 to 500 million years onwards. Over time, pockets of gas are pulled together by gravity to become more and more dense. These clouds begin to collapse under the weight of their own gravity, with temperatures soaring to a point where nuclear fusion is triggered and the first stars are born. The stars act as furnaces, forging heavier elements from the lighter elements they are made of. The first stars are 100 times more massive than our Sun, 20 times hotter, 10 times more luminous, and they shine ultraviolet blue. These first-generation stars only live for a few million years, and once they burn through their fuel, they die in a hypernova, spewing out an enriched cloud of elements. Then a process of stellar recycling occurs. Gravitational attraction pulls the debris of the previous generation of stars together until a new star is created, which then goes on to create heavier and heavier elements. In this way, every subsequent generation of star creates a richer composition of heavier elements than the previous generation. We are often said to be made of star stuff, and it is because the elements that make us have been forged within the guts of these stars. Gravitational attraction creates not only stars, but also the other structures we see in the night sky. Galaxies, groups of galaxies, clusters of galaxies, and superclusters of galaxies. Solar system formation, 8.5 to 9 billion years. Our Sun is a 1,000th generation star, and matter coalesced around it to form the planets, asteroids, and comets of our solar system. Present day, 13.8 billion years after the Big Bang event. Stars continue to die and be created, and the universe continues to stretch. In fact, the universe is stretching at an accelerating rate, owing to a curious form of energy called dark energy. Like dark matter, dark energy is shrouded in mystery, and many predict that the physics of the future will be focused on trying to learn more about the darkness in our universe. We have now come to the end of our journey, having worked our way through the entire evolution of the universe as described by the Big Bang Theory. Please note that the timings are approximations and some events mentioned in the different epochs did overlap. As always, I hope you enjoyed this video, and please subscribe to London City Girl for more interesting and educational videos from me.